All right, so now it's recording 15-second intervals. All right, so it's going. I can't promise that the tapes are going to keep recording. Fortunately, as I sort of stated last class, you have all my previous lecture videos, so you can watch those, and I'm not really necessarily going to be lecturing all that much this semester. Anyways, what I'd like to just get up here and do is just teach you guys what I want to teach you guys, and you guys can learn all the material that I've talked about in the past on my videos online. But today will really, in our classes, will really be days in which we can really develop skills and hopefully get you guys to a point that you sort of understand organic chemistry and not just what you've learned, but hopefully you can continue to learn, because I think that's one of the big aspects of it. Now, one of the things that I didn't get a chance to discuss last week that I would like to do for starters, and then I can open the floor for questions, and then maybe throw some problems on the board. But I may have alluded to this last week or last class, excuse me, that when we think about organic chemistry, one of the things that happens, right, is that we have to do, you learn in first semester how to draw molecules, you sort of learn line angle notation, you start to learn how to rotate molecules in 3 dimensions so that you can look at them in different perspectives, right? You start learning about orbitals, right? And then you begin to start learning about reactions, right? And part of the way that you learn about these reactions is how they work and their mechanisms. And then from all those reactions, then you guys end up tying them all together to do synthesis, right? So there's a huge stream in really what amounts to oftentimes 2 semesters where you're really starting from the ground floor, not even really appreciating how synthetic organic chemists draw molecules. And by the end of actually your first semester and going on to certainly the second semester, you are expected to not only know all these reactions, you're expected to know the mechanisms for all of them, you're expected to be able to look at a new reaction and understand the mechanism of that. And then if that's not bad enough, right, then you're expected to be able to come up with synthetic pathways to generate these molecules. And it's obviously, it's a significant challenge. But I think the important point that I try to drill to students, it's still recording, 3 minutes in, so hopefully we'll be able to get this online, that it's not necessarily every reaction that you learn. If you sort of start thinking about those reactions, the reason why you have to know mechanisms to know these reactions is that you can start to think about these reactions. You might learn 100 different reactions, right? And if you view each of those as their own individual entity, first of all, you might miss the sort of forest for the trees, or trees for the forest. I forget exactly how the term's supposed to go, but the point is that you sort of look at it. Like yesterday, people were asking me, I showed a 5-member ring here, and then I showed a 6-member ring here, and I was just like, well, it's just 2 different molecules. The important point was really as we went through the mechanism, right, it was that sort of silent and the ether and the sort of alcohol. That's where all the chemistry was taking place. The extra couple carbons down below really weren't doing that much, and unless you really focus on and understand the chemistry, sometimes it's difficult to necessarily see those differences. And so you see one reaction and you make one little change to it that really has no bearance on the chemistry, or maybe it does have a bearance on the chemistry. But a lot of times it can be challenging from that standpoint. So, but what I hope to sort of teach you guys and sort of show today and maybe demonstrate today, and the point that I want to make of today's lecture, is that virtually every reaction, I would say 90% of the reactions that you guys are going to learn this semester are really some derivation of a few key reactions that you learned last semester, right? The very first reaction that perhaps you guys learned, it's certainly something that you've seen as far back as, high school chemistry courses, is acid-base chemistry, right? So one of the first questions that's often asked and one of the very first mechanisms that you get is simply acid and base chemistry. And so, you know, any base that you have, right, you can sort of think about Bronsted acid base chemistry, where we're talking about protons moving back and forth, right? It's probably one of the maybe Lewis base might be the simplest, but when we think about, well, actually, yeah, let's do that. Let's switch it up a little bit. So let's start with Lewis acid, Lewis base, which is perhaps the simplest of really any mechanism that you guys can learn. What's the difference between Lewis acid, Lewis base, and Bronsted acid, Bronsted base mechanisms? Anyone? Yeah?
Bronsted with proton.
Yes.
Mm-hmm.
Right. But at the core of everything, as I hope to convince you guys today, if you don't already know, is that electrons are really at the core of anything. So even if you're saying protons are involved, it's really the electrons that are doing the driving behind all of this, right? So standard Lewis acid, Lewis base mechanism, an example of that would be, say, for example, ammonia reacting with borane. Right? And so when, say, ammonia reacts with borane, what's going to happen in this reaction? You have boron, which drawn in a horrible sort of geometry there. We can certainly talk about the geometry. This might be a good time to mention it. What's the hybridization of that nitrogen? It's sp3. So what's the geometry of that? Right, it's tetrahedral. As we'll talk about later on, and some of you that came to my office hours yesterday sort of know that oftentimes when you have that nitrogen, it's a lone pair. In this case, it is an sp3 lone pair. Sometimes as we'll see, it can actually turn into a sp2 lone pair based upon resonance forms. Now, what about borane? What about BH3? First of all, what's the hybridization of that? So sp2. So why, those of you, somebody that said sp2, why is borane sp2? It's only got 3 things bonded to it, just like ammonia, or does it? Or maybe you could think about ammonia as kind of a quote-unquote fourth bond. It's not a bond per se, but it's got electrons that are occupying a fourth site, which is the lone pairs. The borane doesn't necessarily have that, right? And so because that's an empty orbital, how do we think about things hybridizing, right? Everything's going to want to try to get as far away from everything else as possible. So what's going to happen to that extent is that all the hydrogens are going to try to get as far away from one another as possible, and that takes place when you go into the sort of two-dimensional sp2 state. All right, and now borane is sp2 hybridized, which means that there's the extra p orbital. Where is that occupying? Right, that's becomes that sort of vacant orbital there. So again, the reason why boron, in general, it's in its neutral state, it's only got 6 electrons total. One of the reasons why it wants to be a Lewis acid, and one of the reasons why it wants to accept electrons, right, is that it would like to have a totally filled octet, right? And so what happens in this mechanism? The lone pairs, the electrons, right, go from sort of the nitrogen, right, to make a bond with the borane. So the lone pairs are effectively going to dump themselves or begin to share themselves with the empty p orbital of the boron. That's now going to make the boron become sp3 hybridized at that point, right? Because now this will be a sigma bond, right? We can draw that this way as well. And the product that we have right, where the lone pairs that we draw here, right, are now making the bond with the borane. What's the charge on the system now? Positive on what? The nitrogen, and negative on the borane, right? And so now, you know, certainly during the beginning of last semester, and maybe for some of you guys now, when I asked that question about charge, some of you may have to count up the electrons, look at what it's supposed to be. But the other thing is, I mean, you look at this and you just think logically, right? If this is accepting an electron, it's going to become a negative charge. If this is giving up an electron, it's going to be a positive charge. So you can go ahead and you can keep counting, and maybe that's a good double check, but hopefully eventually you guys get to the point where you recognize that if I'm accepting an electron, I'm going to become negatively charged. If I'm donating an electron, I'm going to become positively charged. Or I'm going to change my charge state plus one direction or the other. So this is perhaps the simplest example of any mechanism, right? It's a single arrow. It's a single electron that is moving from the lone pairs of the nitrogen to make a bond with the boron. It doesn't get any simpler of a mechanism like that. Now notice what is important, and again, this is second semester organic chemistry, so I hope for the vast majority of you this is not something I need to tell you, but it's really, really, really important that you recognize the direction in which this arrow is going, right? Notice that the electrons and the arrows are moving from the electron in the direction in which case they are going, where the bond is being formed. Oftentimes, and this goes back to what we discussed yesterday or 2 days ago about, you know, misinterpretations of mechanisms. I can't tell you the amount of times that students have been messing up a mechanism, and I start to ask them what this arrow means, and they say, oh, it's a bond forming. And yes, it's a bond forming ultimately. That is the nature of what is ultimately happening. That is the end game of those electrons moving. But what the arrows actually physically mean is they are the direction of the, it's the direction to which those electrons are going. I've often sort of joked that that if I see arrows going the wrong way, right, like, you know, I'll the quickest way to like lose all the credit on a question. I'm not joking about that. That's serious. It's the quickest way. If I ask you guys a mechanism and you start showing the arrows going in the wrong direction, you know, when I ask you guys mechanism questions, I'm probing and I'm testing your ability to actually understand the foundation, or the fundamentals, of mechanisms. That's why yesterday I was saying I'd rather see a mechanism that gets 80% of the way there, and every single step along that way is solid, rather than some crazy-looking mechanism where you're just pushing things around that happens to get to the end product. Like, I don't want to see that. That will get, latter one will probably get 0, and the former one might get 80% of the points or something like that. So, again, it's important that we understand what these arrows mean. It's important that we are able to track where those electrons are coming from and where they are going, and that is specifically what those electrons mean. And so again, Lewis acid, Lewis base is perhaps the simplest of any mechanism that you're going to see, right? Because it's just one electron, one arrow. Bronsted acid, Bronsted base is probably the second easiest mechanism. Again, the difference between Lewis acid, Lewis base chemistry, and Bronsted acid, Bronsted base chemistry is that now we're referring to protons, right? And so if instead of, say, for example, ammonia reacting with borane, it would be equivalent to, say, ammonia reacting with, I don't know, acetic acid, right? So right? So this is ammonia again, and that's acetic acid. And again, we know that ammonia is fairly basic. We know that acetic acid is an acid, and so we know that these are going to react together. pK of ammonia is what? 10, 11, in that ballpark, right? Somewhere in that ballpark, maybe a little higher, maybe, I think it's 10. You guys know ammonia? Is it? What? Somebody said a point, which means that they really know what it is. 9.2, Berkowitz. All right, and acetic acid is 4.75. Yeah, somewhere around 5. So the point is that this reaction is going to take place. It's going to be thermodynamically driven to react with one another. But in this case, you can't do. These lone pairs aren't just going to be able to go and immediately make a bond with that proton. What is going to happen if you stop the mechanism there? We're going to have 2 bonds to hydrogen, right? And what's the problem with having 2 bonds to hydrogen? There was a paper recently where somebody had done that. I think. Not like really do it. It was like a glimmer of it or something. I forget it. I remember it came out. They're like, oh my god. Or maybe it was like 10 bonds to hydrogen. Maybe that's what it was. It wasn't 2 bonds to oxygen. Or sorry, it's 2 bonds to hydrogen. But again, yeah, you can't do it, right? Because hydrogen, we learned about the octet rule, right? The octet rule basically says that the valence shells of sort of second row where you have carbon, right? There are only maximum space in those valence orbitals for 8 electrons total, right? So this is one of the reasons why carbon can't exceed the octet rule. And if you exceed the octet rule, you'll lose all the points on that question. Another example, like your arrow going the wrong way. But, so that's the octet rule, and that's going to be consistent with carbon. It's going to be consistent with nitrogen, oxygen, boron, all of those guys on that end. But above it, you have hydrogen. And what are hydrogen's valence shells? It really only has the 1, right? It only has the S, so it really only has room for 2 electrons. So hydrogen is not going to be able to accommodate an additional 2 electrons. So what has to happen at the same time? Yeah, so simultaneous with bond formation, you get bond breaking. So this is a concerted process. Both of these things are happening at the same time, right? It's not a stepwise process. It's a single process, and the net result is that now you have nitrogen with those blue electrons has made a bond with, say, that hydrogen, right? And the lone pair on oxygen, or sorry, the electrons that were in that oxygen-hydrogen bond have now become an additional set of lone pairs for this oxygen. And so, again, you would have 2 others here anyway. You have the 2, and then you have the 1 more set. So again, if you want to go ahead and count all these, you would see that this oxygen now has 7 electrons that it sort of owns. 6 is neutral, 7 is -1. If you look at nitrogen, nitrogen likes to have 5 in the neutral state. It goes to 4 because it's giving up 1. That's +1. But if you simply look and you know that this is right, even if you don't want to count those up, you see that, again, this nitrogen is giving up an electron, so the change is going to be positive. In this case, that oxygen is going from sharing the 2 electrons to now owning them itself, so it's taking on an additional electron, and so this is going to become negatively charged. Okay, so here's, again, the 2 acid-base mechanisms. Lewis acid, Lewis base, Bronsted acid, Bronsted base. Single step, right? So boron, you can do this with boron, right? Because you're not breaking the octet rule with boron. It's one of the examples that you can actually do a single arrow mechanism, right? Because you would need to be able to dump electrons into a system in order to do something like this, right? You would need a system where it can take on 2 electrons and not break the octet rule. So most of the time you'll perhaps see concerted processes. In this case, you need the concerted process because hydrogen is not going to be able to have 4 electrons around it, and the same reason that, say, carbon's not going to be able to have 10 electrons, at least valence, around it, okay? All right, so these are sort of 2 of the first couple reactions that you guys should all be able to be familiar with. You then move on to substitution. And what is substitution? Except for a variation, right? So I can even then convince you now that every other reaction that you've learned are some variation of those 2 reactions that you've seen, right? So what is substitution but a sort of extension of really acid-base chemistry? What is happening, right? If you think about it, right, what is happening with Bronsted acid, Bronsted base chemistry? That hydrogen is having an acetate substituted for an ammonia, right? And so this is the parallel between Bronsted acid, Bronsted base chemistry and substitution chemistry. The difference is that generally when we're talking about substitution chemistry, we're not talking about protons, we're talking about carbons, right? Because this is organic chemistry and most of the reactions that we're learning about involve carbon. Now, in substitution chemistry, obviously we can break it down. We discussed this a little bit yesterday, that you can break it up into 2 types, right? So you have your exact parallel to Bronsted acid, Bronsted base, and that would be SN2, right? And so in an SN2 reaction, you would have, to show an example of an SN2 reaction, usually what would happen is you would have, in this case, the leaving group is an acetate. Certainly you can have an acetate leaving groups. They're not the best leaving groups in the world. Usually, what are the common leaving groups that we see a lot of? Halogens, right? Bromine, chlorine, chlorine's so-so. Certainly bromine, certainly iodide. We'll see chlorine a bit as well, but bromine's a really good one. Iodide's a really good one. Did you guys learn about triflates yet? Maybe not. Tosylate, okay, so we'll learn about those, I think, shortly. But yeah, in general, the go-to leaving group that you guys have seen are halogens, particularly bromine. Bromine is the most common, I think, leaving group for anything. So bromomethane, actually bromomethane is, I think, a gas, so people don't use it, so they would use iodomethane. But at least in textbooks, you'll see bromomethane. But let's do iodomethane. Actually, no, let's do let's discuss the difference between substitution and elimination. So substitution and Bronsted acid, Bronsted base. So in an SN2 transformation, right, it's going to be concerted, but we're hitting a carbon. And so while hydrogen, inherently by the nature of it being a hydrogen, right, there is no stereochemistry at a hydrogen. But clearly if you have a carbon and you have certain substitutions and they're not all the same, if you have stereochemistry here, as you guys know, in substitution chemistry, there can be a stereochemical impact of that transformation. And so if you were to take a nucleophile, give me a good nucleophile, someone?
N3 minus.
Second?
N3.
N3? Sure. And then that will allow us to discuss why N3 is a good nucleophile. So what are the reasons why an azide, so it's called an azide, right? Why is an azide a good nucleophile? Because what? Because it's linear, right? It's not sterically bulky. It's got a charge on it that it could potentially use to neutralize. So yeah, so you see a lot of the really, really good nucleophiles are these sort of sp, this is, I guess this would be, so this is certainly sp hybridized, right? Never really thought about the hybridization of that. What do you guys think? It's probably sp as well, right? Because of the resonance form. I actually don't know. Let's assume it's sp hybridized, but you'll see that a lot of them are sp hybridized, right? Because the resonance form, we'll get into that in a minute, because the resonance form can basically put that negative charge on either side. Oh wait, no, because then if it went to the other side, Yes, thank you. That's why it doesn't make sense. Yes, good catch. So yeah, I was like, what's going on here? So yeah, I don't know what the. So it probably is sp2 then. Anyways, but the point is that I never really thought about the hybridization of an azide. But again, it is linear. It is. It is sort of, which makes it small. It's got a charge on it, an overall charge that's negative, which can allow it to attack. And in this case, in an SN2 reaction, everything takes place simultaneously, right? And because of that, we get what we sort of call sort of backside attack, right? Now, one of the questions that we can sort of ask here is, why does it attack from the direction that we're attacking it on? It's one of these things you guys learn on nucleophile backside attack. Well, why are we attacking from that direction? Does anybody know? Anybody have some ideas that needs to think about? Yeah.
So the leading group has a relatively the angle will shift.
So, well, yeah, I mean, that's, so I think what you're kind of referring to is the intermediate might be the most spaced out. Maybe that's kind of what you're getting at too, is overall the structure would be sort of, you have a planarized. Right, so it's maybe the way that you could spread everything out the best. That's a decent reason to think about it. What are maybe some other reasons for this? Yeah.
Because the carbon only has a partial positive charge.
So okay, so the carbon certainly could have a partial positive charge on it, but it could certainly be. There's still other directions. It's about the directionality of it. Yeah.
This is sterics.
Well, that's kind of what was brought up about this with sterics. Yeah. Yeah. What were you gonna say? So that's what's being brought up as sterics. But what's your name? Natalia hit it on the head. The antibonding orbitals, right? So every bond that we have, right, we are going to have, you know, we learn about, I don't know how much you guys went into in terms of orbitals, molecular orbitals. We'll go into them specifically. I spend a lot of time talking about them, for example, when we discuss pericyclic reactions, but certainly in substitution chemistry, I mean, orbitals are where everything is taking place, right? Previously, I showed you guys, and we discussed about how Lewis acid, Lewis base chemistry, the lone pairs had to attack the empty p orbital, right? And that's where it made the bond. Well, now the question becomes, well, where's the orbital that this is? Where are those electrons? Where's the orbital those electrons are going to go to? It has to start filling an orbital. Right? And any time you look at these generic, you know, molecular orbital diagrams that people have where, you know, you have some bonding orbital, and this can be very, very generic, right? But you have two electrons that are binding together, and they form a sigma bond, right? You guys have probably seen these in the past, right? So they form together, they form this bond, but there are basically two orbitals being brought together, so you have the bonding orbital, and then you also have the antibonding orbital. And so this is what would otherwise be referred to as the sort of sigma star, right? So for every bond, if this is, say for example, a carbon-carbon, this is sort of the two coming together, right? The antibonding orbitals are kind of the opposite of that. It would look something like this. And so this is where those electrons are ultimately going to go to. They have to go to this sort of antibonding orbital, and the antibonding orbital is, at least for sigma bonds, is 180 degrees away from the bonding orbital, which is back there. Okay, so that's at its core. That is certainly sterics. You could argue maybe a component of that, and I think that's a good answer, in part because you can rationalize it. But the real truth of it is it has to do with antibonding orbitals. So this is one of the areas where molecular orbitals can hopefully help you sort of understand and appreciate that. Okay? All right, so because it has to come through the back side, right, you're going to go through sort of an intermediate, such as the one that I've shown you here. So that would kind of be the transition state, if you will. Still recording. So did Mondays. And so in this system, right, you have this I've sort of drawn it as a negative charge here, but really what you kind of have is a delta minus. You guys know what that means when I say delta minus? Delta, yeah, it's a partial charge, right? So this is sort of something that's really important, that you recognize that this overall, this, again, conservation of mass, you can't disobey conservation of mass, you can't disobey conservation of charge, right? This overall system here is -1 charge. This overall system here is going to have a -1 charge to it. You've got negative charges here and here. You probably have a little bit of delta positive charge in there as well, right? And so, but it can go in the reverse direction. It can also go in the forward direction. And when it does, you're going to lose the bromide. And you are going to generate, in this case, your azide. Now, it's often said, right, that in this reaction that we are inverting stereochemistry. Now, here's another thing that where translation can become a problem. I often hear students, they make the assumption that if something is going to start as R, that inversion of stereochemistry means that the product will be S. And maybe they see a few examples where they see that and they get it in their head, inversion of stereochemistry, R becomes S and S becomes R. No. R and S are simply descriptors of stereochemistry and are simply a way for us to describe the stereochemistry around a carbon. They mean nothing besides the description. That's one of the reasons why I hate, it doesn't matter what a molecule is R, it doesn't matter if a molecule is S, that has no bearance on the chemistry of that. Well, it can, but the fact that we call it R, the fact that we call it S, doesn't, right? R and S, I always think R and S type examples, one of the reasons why R and S in the first semester of chemistry, that you have to solve R and S is because of the fact that oftentimes determining R or S requires you to perhaps rotate the molecule around. If you start doing all these little tricks where you switch this and that, and you get your RS, great, you know that it's RS, but you haven't learned anything, you haven't worked on rotating molecules, you haven't practiced that skill, which is foreign to you guys, such that when you start doing mechanisms, now you can't do it. So if you're one of those people that did lots of tricks and you were really good at solving RS, congratulations, you got a few extra points on the exam. Hopefully, it didn't stunt your growth of being able to redraw molecules in different orientations. That's my little comment there. But anyway, so here's an example, right? This, you have quote-unquote inverted stereochemistry. All that it means when we're saying inverted stereochemistry, which could be confusing, is that the side that the leaving group was on, the sort of nucleophile is just going to be on the opposite side of that. That's ultimately what it means. To say R and S doesn't really capture that. Okay? So this is an SN2 reaction. Again, parallel to Bronsted acid, Bronsted base, but with carbon. Anything else we want to say about this? Obviously now we know, yeah?
Why is there a transition state if it happens in a conservative fashion?
Say that again?
Why is there a transition state if it happens in a conservative fashion? Whether we use or
So transition, so concerted versus non-concerted does not mean there's not a transition state. The transition state is the energy barrier, is the sort of the maximum energy that it requires to have the transformation form. The difference, it's always going to have a transition barrier. A non-concerted reaction will probably have two transition states. It'll have a transition state to one intermediate and then a transition state to the other intermediate. Does that make sense? Okay. Okay, so SN1, given the time, hopefully you guys sort of know SN1 is simply a two-step process through this. Again, your book discusses lots of different rules of how to think about SN1 versus SN2. I think one of the most important things about that is stability of cations, things that lead to stability of cations. So maybe it's worth it to just sort of mention this really quickly. We discussed yesterday, and there was a little bit of confusion, and a lot of people came up to me afterwards asking about, well, why can you explain this idea of stability of carbocations, right, based upon substitution around there, and sort of idea of sort of hyperconjugation. But again, that's just one of the more important things to sort of think about is what is going to stabilize a cation, right? right, within SN1, and how might that dictate whether an SN1 is going to take place? I'm not even going to spend time on that because I'd like to discuss some other things and then open the floor for some questions for you guys. But, whether a reaction goes through SN2 or whether a reaction goes through an SN1, it's probably important that you realize that a tertiary, if you can generate a tertiary carbocation, not going to go through SN1 it's not going to go through SN2 because of sterics, right? And because that transition state to generate that carbocation, the first transition state where you actually, or the first intermediate, I should say, of the carbocation is stable, right? Primary, you're never going to generate a primary carbocation. Sterically, it's wide open, so that's always going to go through an SN2 transformation. And then when you get to secondary situations such as this, then you sort of look at it and you weigh all the options and you try to come up with a hypothesis of which one of those two it would go through, and maybe that'll have an indication on, say, for example, stereoerosion, right? If you have a single enantiomer here, and suddenly you've got 100% EE here. You guys know what EE is, enantioselectivity? Let's just say you have 100% of one enantiomer here, and then suddenly here now you've got 70% of one enantiomer and 30% enantiomer of the other. What would be an explanation for that? You got a little bit of SN2 going on, you got a little bit of SN1 going on. The SN1 is leading to a racemate. The SN2, competing SN2 pathway, is keeping the enantioselectivity such that it's not racemic. It doesn't become a 50-50 mixture. So that's what something like that might tell you. Let's move on to elimination, right? So I'm trying to think, should we do elimination first? So when we get to reactions like elimination, and again, in this case, we'll start with E1. Again, I don't really care that much at this point about whether you know if something's going to go through an E1 or an E2. But I do want you guys to be able to draw elimination mechanisms, understand specifically for E2 how there is also stereochemistry, actually for both E1 and E2. There's often stereochemical outcomes that can take place between both of them. What I would prefer to have happen in this case is if I gave you a mechanism and I asked you, for example, why this might lead to the stereochemistry that it would in a specific elimination, I'd like you to be able to come up with the reason based upon that's not simply hand waving, that's actually based upon the principles of chemistry that would explain that. Again, we know that in an E1 reaction, one of the keys of being able to do an E1 reaction is obviously going to be, again, the ability to have a stabilized carbocation, and that's really where I'll start and end with that. But certainly if you have, say for example in this case a bromine, and I'll put R2 and R1 here, which will just be like this. Right, in an E1 reaction, in parallel to the SN1 reaction, the first step is going to be the leaving of, so in this case we're going to have a base in here. Again, the stronger the base, the more likely that it'll be inserted. If the base is in fact driving the ultimate leaving, right? It's sort of like if the difference between E1 E2 is really whether the bromine wants to leave first or whether the sort of electrons sort of push it out, if you think about it that way, right? That's kind of the difference between E1 and E2. And so if you have a stronger base that's going to want to really react with the proton, or if you have a really acidic proton that might more likely be protonated, these are going to be things that might drive E2 elimination. If perhaps you have a weaker base or a really strong leaving group and the cation is going to more likely want to form, then you're more likely going to go through an E1. But in truth, it's sort of in between, and it's just important that you look at the overall picture and try to come up with a reason behind it. In this case, for this elimination, maybe we'll choose a fairly mild base, something like maybe pyridine, which has a pKa of about 5, as we discussed yesterday. So not the strongest base in the world, but certainly basic. And at the end of the day, the pyridinium bromide is going to certainly be a stabilized molecule here. So if we have pyridine, and we drive this reaction, but I'll just tell you that because of the nature of, say, for example, R1 and R2, let's say, for example, the bromide leaves first. Now, one of the things about elimination chemistry, right, is that once you do that elimination, again, what's going to happen to the nature of this carbon geometrically? You're going to planarize, right? So you're going to leave. You're then going to have an empty p orbital. What's going to happen to the R1 and R2 when it leaves? They're going to stay in the same direction. And again, depending upon, when you eliminate, you get to this local intermediate, there is the possibility now for bond rotation, right? And so what ends up happening here is, again, you have your positive charge here on this empty p orbital, but you can certainly begin to get rotation around that bond, which you could have done previously anyways, yeah. Say it again?
You're still showing the stereochemistry even though it became
So yeah, well, I mean, there is this, so let me show you why it's important, right? So I've got R2 here, I've got R2 here, they're on the same face of the board. It's important that we keep R2 and R2 on the same face of the board here. The thing is, with this though, is we could have left the bromide at either position. So in principle, from this intermediate, I guess this is kind of what I'm saying, is that if this gets down to, if I were to draw the other one, in terms of answering the problem right, it wouldn't have made a difference, but this gets down to, what did I show? I only showed the bromine leaving. So why am I going to then start making other changes? Right? So you should keep things as consistent as possible and only show the changes that you did. So the stereochemistry isn't important, I think, for answering this question, as I'll hopefully convince you guys. But I think it is worthwhile to really try to stay as consistent when you draw things as possible. All that I've done here is had the bromine leave. So if I start switching the R1 and R2, well then I've done something else here too, which it might not seem, and it turns out being trivial for the sake of this specific question and getting it right, but it's a good practice to get into to try to stay consistent. Right? So this is what I was getting to previously, is that this could rotate back and forth. Right? So that would help flip those R1 and R2 groups. And so in principle, you could have either one of these molecules. And again, the difference between these two are the relationships between the two R2s that I've drawn and the two R1s. So in this case, the R2s are on the same side of here. On this side, the R2s are on opposite sides. Now, as we know, with the vast majority of molecules, rotation is fairly free. Right? Rotation is fast, it's going to happen really, really quickly. And so this rotation could take place here, or it could have taken place here. But from the elimination standpoint, a lot of the things with E2, you have what's in essence, two molecules that are simply rotational, just different in terms of configurations of the same molecule. But what you notice here, though, is that the subsequent step of the elimination, right? So the first step is the same as an SN1. The second step is an elimination. Okay, so when we do that elimination, say the pyridine comes here, or the pyridine goes here. Those lone pairs are going to make a double bond, right? So in the case of an E1 reaction, in principle, you can get two products Okay, now I'm showing them, somebody was asking earlier about the stereochemistry, right? I've simply, this is obviously, an alkene is obviously planar, right? I have simply drawn this molecule coming in and out of the board. You could just as easily draw this going this way. There's two different ways to draw the same molecule. But you'll notice that the two groups are on the same side there. If I draw planar, they're on the same side as well. So it's important that you show the stereochemistry in one way or another, whether it's planarized or whether you show it coming on the board. And I think as we'll discuss in an SN2 reaction, sometimes it's a lot easier to draw alkenes and see stereochemistry when you do draw them this way. I just find it a lot easier because a lot of the chemistry is taking place. As you can see, the chemistry is taking place in the plane of the board. Sometimes it's easier to see the chemistry in the plane of the board and put the substituents sort of coming in and out of the board. But this is one stereochemistry, right, where there's your pi bond, and in this case, right, in this case we're going to have different stereochemistry. So I'll just go right to the planar form here. So in one case, the R1 and the R2 are the same side. In the other case, the R1 and the R2 are opposite. So knowing that this is the mechanism through which these transformations take place, we haven't really defined what R1 and R2 are here. But, yes? This is an E1 reaction. These are the two possible, and I haven't defined what the products are, but you can clearly see that either one of these can form. But they're different molecules, and they're sterically very different. The intermediates are very different. And so what do you think the factors are going to be that might influence the ratio of this, right? If R1 and R2 are drastically different sterically, if R1 is, say, a methyl group and R2 is going to be a T-butyl group, what do you think you're going to get as the product? Yeah, you're probably going to want the two T-butyl groups to be really far away from one another. Why? Well, the product would certainly be more stable. This would be an intermediate that would be a lot more stable, so the elimination from this intermediate would be more stable, right? If you had, say, for example, an ethyl and an N-propyl, which are sterically almost identical, what kind of result might you expect to see here? Yeah, maybe like a 50-50 mixture of the two. You get sort of a lack of selectivity here. And so again, it's important that you sort of understand the mechanism, and then you sort of look at the bigger picture of well, why are we sort of getting what we are getting, and sort of how might we think about this? Okay, now E2 is a little bit different, because in E2, you're never going to leave that bromide, and it was asked previously about the importance of stereochemistry. Yes, we are planar here, right, so we can fully rotate around that, and it's equal, you know, the empty p orbital is the same on both sides, so you know, there's, absent from changes here, the, in fact, energetic difference of just deprotonating and eliminating are going to be the same. However, in an SN2 reaction, sorry, E2 reaction, it's one wherein the base, maybe it's a stronger base, the carbocation isn't going to be as likely to form. And so in that case, I've sort of drawn it already set up for it. But how does an elimination, let's see if you guys remember, how does an elimination in an E2 reaction take place? Anti-coplanar, anti-periplanar, right? So they're on opposite sides of one another, and they're planar. They're in the same plane. Why? So you can either memorize, oh, they have to be anti-periplanar, right? Or you can try to understand electrons and orbitals. So why does an SN2 reaction, let's go back to that, somebody that didn't answer previously, why does an SN2 reaction proceed through backside attack? Yeah. Antibonding orbital. Putting electrons in the antibonding orbital. Now where's the antibonding orbital in this? Yeah. Where are the electrons on that hydrogen that are going to put those electrons in the hydrogen closest to that bond when it's anti-periplanar? So in an elimination reaction, it's also about the orbitals. We just have to look a little bit further away. But we want the transition state, in which case we're going to start getting closest to the product. So you look at that sigma star. You look at how those electrons that are ultimately going to get into it, right? What is that called? If a lone pair is, sorry, not a lone pair, but if a set of electrons is, I think from last class, if a set of electrons in a bond are sort of being pulled towards an empty orbital, sort of hyperconjugation, right? Generally we think about it for carbocations, but here's a similar type of situation where there's an NPP orbital, maybe those electrons are being pulled in that direction, and then a base comes in that happens to be strong enough, let's say T-butoxide, and you get that elimination. And so in this case, again, looking at the stereochemistry, the nature of that elimination is going to be that nothing is going to change, right? In this structure, as is drawn, the R1 and the R2 are on the same side of the molecule, and so in the product, they're going to stay the same. And this is, again, why I like drawing coming in and out of the board. R2, R1, R2, R1, right? And so if you were trying to, let's think about synthesis type problems, if you wanted to make an alkene, but the alkene that you were looking to make was, say, for example, the thermodynamically less stable of the molecules, are you going to want to try to make it through, and you want to use elimination, are you going to want to go through an E1 pathway? If it's not the thermodynamic product? Probably not, right? Because if it's not the thermodynamic product and you're trying to do an E1 elimination, the chances are it's either not going to be forming at all, or it's going to be a minor product, the best case scenario equal. So you would try to set up a situation with a halogen where the proton can rotate around such that when you have the bonds antiperiplanar, say the groups that make it less stable will want to be sort of closer to one another. Okay? All right. So that's substitution. Acid-base. Right? Oh, sorry, acid-base, substitution, elimination. And then the last sort of comment that I'll make is that we've shown these reactions, and this will just loop back to one other chapter that you learned last week, and that's that, you know, every single reaction that we've sort of described, every mechanism that we draw is at least in theory reversible, right? When I drew previously that pyridine, or sorry, that ammonia, excuse me, reacting with acetic acid right? If I drew this reaction, right, certainly the reaction is going to be driven in this direction, right? But it's still reversible. You can still also draw it in the reverse. Maybe it's got a little bit of a lower equilibrium arrow. You know, maybe there's 1 million pyridines for every pyridinium, right? But there will be some slight equilibration. If you take 100%, 100.000000% of this, it ain't going to stay 100.00000%. It will equilibrate to, what would we say the pK difference between ammonia and that are? About, what was it, about 6 or so? 5, right? So that means that it's 10 to the 5th. You know, if you've got 10 to the 5th of one, you're going to have one of the other. So that's going to sort of be your ratio in essence of those. That's just a quick back of the envelope. But you hopefully get the point, right? So, again, last semester, you guys learned about alkene chemistry. And when we think about alkene chemistry, what is substitution, for example, of an alkene, then the reverse of an elimination reaction, right? And so when we think about what's happening here, right, we're generating, say, for example, HBr is ultimately the product. In this case, it's a T-butanol and Br minus. But if, let's just remove the T-butanol together and just say that we're eliminating HBr here, right? What happens when you take an alkene and treat it with HBr? It's the exact opposite of what we just saw there, right? So first step is going to be protonation, right? And then you're going to generate carbocation somewhere. So this would be more a reverse of the E1 transformation than the E2 transformation. But therein lies the sort of point, is that every single mechanism, or I would say until we start getting to, say, transition metal chemistry, which represents kind of new classes of chemistry, pretty much every single reaction that you guys learn throughout this entire semester, mechanistically, will be some combination of, or related in some fashion to a reaction that you've already seen. And your goal in this class, the first time that you see any reaction, you should ask yourself, can I think of this before looking at the mechanism? Can I come up with this mechanism before I look to the book and see what it is? Can I come up with it based upon what I've learned? And if you can do that, there's going to be very, very few. We're going to learn another 60, 70 reactions this semester. You might only learn 5 new ones, right? Does that make sense? So again, really try to relate every single reaction that you see this semester to this. Oh, one other point, because it can kind of trip people up a little bit. This is a little bit more advanced one, but I know you guys have already seen it, so I'll bring it up because I think it sort of serves a point that we saw previously, and then I'll, basically out of time, but we'll have maybe 10 minutes if somebody has a question. But I'll make one quick point, because there is one other little tricky thing that I know you guys struggle with sometimes, and truthfully, we don't, as synthetic organic chemists, it's not something that we think about that much in our labs as well. You know, certainly you can be clever and fancy, and there are potentially very valuable uses for this chemistry, but it's not something that we necessarily plan for. But you guys do learn it, and it's sort of cation-mediated rearrangements, right? And so one of the things that we discussed last class was that when you have a cation, if you have a proton or a methyl group or some alkyl groups next to it, you can get hyperconjugation. Right? And in essence, what hyperconjugation is it's the electrons that are sort of in the closest possible planar, right, orientation, as close as possible to that p orbital, start to give themselves a little bit to the adjacent guy, right? So there starts to be this little tug that helps stabilize that charge. It's the same thing with, and so that's the more of those that you have, the more stabilizing that you can get, right? Yesterday in my office, we started talking about, say for example, stabilization of alkenes. It's like it says rule. Why is a more stable, so we just discussed sort of alkene, stability. And as you guys probably know, and maybe you just memorized, right, that when you have an alkene that has more substitution to it, it's generally a more stable species, right? And what's the reason for that? It's the same thing. Hyperconjugation. Now, it's not going to be stabilizing a positive charge, and this might seem a little odd and difficult to wrap your heads around, but we spent a while yesterday in my office, and eventually it was like, oh yeah, but so I'll just trust me on this, and we're going to try to figure this out because it does help explain hyperconjugation. Again, we have p orbitals. And p orbitals are slightly higher, right, than sigma orbitals. They can also align themselves, right, with electrons. You know, you're not going to be able to align that proton with a sigma bond, right? You could certainly align it with a p orbital here, right? And what do you have there? You have a back bond. Now, why would it do it? You're not stabilizing a positive charge, right? So it might not make that much sense. But what really drives so much of the chemistry that we see? It's that electrons are, I like to think about electrons, I often say this, that electrons, if I sort of humanize electrons, electrons are like claustrophobic, right? Like they're extremely high energy. If they can, again, resonance forms are a perfect example of this, right? Resonance stabilization is really strong. It's not only strong because it can help stabilize charges, but it's also strong, and we'll talk about this in a month or so within sort of conjugation. When you can spread electrons, even if it's a neutral electron, we can spread those throughout over a system. That has a stabilizing impact to it. And so we're going to learn shortly, for example, that a diene like this where you have all these p orbitals aligned with one another, is more stable than a system where there's separation between those two. So of these two isomers, when the p orbitals can align, and we'll talk about this in a month or so. Same factor here. It all sort of applies to this idea that electrons can sort of, they can align themselves up there so they can help share and sort of donate into this orbital a little bit, and sort of that helps give them a little bit more breathing room, which ends up being a stabilizing effect. So, but again, getting back to that, so that's just a tangent on the nature of hyperconjugation. But another sort of thing you can think about when you see hyperconjugation that can sort of, in a way, provide evidence for hyperconjugation, right, are cation-based rearrangements, right? When we have those electrons being tugged in that direction, what's the extreme of that? Getting pulled all the way over. And again, this isn't probably something that you're going to want to do because you're going to go to a primary carbocation, so it would probably be way in the reverse. But nevertheless, as I stated earlier, everything is reversible, right? And so that is a cation sort of 1-2 migration, right? You guys have seen this, right? You guys saw this with what? I think a lot of times you guys see carbocations, oftentimes you'll see these rearrangements, there'll be these difficult mechanism questions where you'll see your carbon skeleton begin to rearrange. I showed it as a proton migrating. You guys will often see it as carbons migrating. Oftentimes carbon migrating is a little bit, the competition between the two can be a little tricky because I think oftentimes, most cases you'll see carbons migrate, but hydrogens, because they don't necessarily have any directionality to them, it's a little bit easier to align the orbitals in that way, so both can kind of happen. But you guys usually see carbons migrating. But again, that's just another example of sort of illustrating hyperconjugation, yeah. If these were like if these were like CF3s instead of CH3s, would it drive it in this direction?
You said you can't have a positive one.
You're not going to have a carbon, yeah, you're not going to have a positive.
But if there's induction,
I mean, basically what you're asking is, can something drive this in the other direction? So if these were like CF3s, really super electron drawing groups, but that would be a maybe not, because the halogens can donate its electrons back in and form a resonance form. If it was like a CF3, maybe. But again, then you're probably never going to form that carbocation in the first place. Something like that. The CF3s are very strong electron withdrawing groups. So that's what you're saying. And these would certainly destabilize this in a major, 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 major way. And the fact of the matter is you'd probably never generate a cation in the first place. It would just be too high in energy. But if you could, it might. I don't know. That would be something for a theoretician to look at. All right, so there's about 10 minutes left. So again, I know that I've taken some time to hopefully make a broader point about reactions. I'll just, again, reiterate that we are flipping the course a little bit this semester. Go view my videos. But what we're referring to and what you should be focused on learning about right now is the chapter on alcohols. And if there's any specific questions, I can certainly answer them. If not, I can talk a little bit of alcohols. So what do you guys want? Anybody have any specific questions? Okay, so let me, if there's no questions, in the remaining 10 minutes, let me just go ahead and I'm going to introduce alcohols. And again, there's a lot of reactions. You guys can go watch my videos, learn all about the different reactions, read the book, see all them all. Again, what I would highly recommend that you guys do is look at the reaction, look at the reagents, look at the product, and try to come up with a mechanism before looking at the book in terms of what it is. That'll be a really good way to practice the mechanisms. It'll be a really good way to hopefully truly understand what's taking place. But what I'd like to do right now is bump ahead just a little bit, and I'm not going to get into synthesis, but I want to approach alcohols and the value of alcohol chemistry from the standpoint of, synthesis, right? So everything that we've been doing, and everything that we were just talking about, was about electrophiles, nucleophiles, acids and bases, reacting in some capacity. When we look at those alkenes, right, the alkenes can serve as nucleophiles, right, even though it might not be your standard nucleophile, but certainly when it's reacting or it's behaving as a, that's if it's reacting with an electrophile, or if it's reacting with an acid, it's behaving as a base. But one of the unique things about alcohols, right, I think everybody knows what an alcohol is, right? But when we think about the reactivity of alcohols, they are actually, as we'll see, they're one of the more challenging sort of structures to work with, say, for example, in a synthesis problem. And part of the reason for that is also the benefit of them. They have a lot of versatility to them. Alcohols, as we will see, can serve as a base, right? It has lone pairs on them, right? And so it can certainly serve as, these lone pairs can help it serve as a nucleophile or as a base, right? So what's the pKa of an alcohol? On this end, if we want to protonate it, so 16's on the deprotonation. I'm talking about to have the lone pairs get protonated. What's that pKa? It's more acidic, right? So again, think about the 0 to 14, right? It's going to be a little bit below 0 because that's when water starts to become protonated on the pH scale, so you can't measure those. Right, so yeah, it's about, pKa is about -1, -2 in that ballpark. And so what kind of acid would you need to protonate water? Something that's stronger than that, right? You're talking about your sulfuric acids. You're talking about, how HBr and HCl, right? When you talk about HBr and HCl solutions in water, right? We don't think about it. HBr or HCl, these are gases. And certainly you can see the gas singe your nose hairs and stuff like that. But in reality, what's in that solution is H3O plus X minus, right? It's also another reason why HF does not. It's not ionic, and it can actually go through your skin because HF is a little bit different. It's got a pKa of about 4 or so. So it's not quite as acidic, so it'll exist as HF and it won't ionize. But yeah, if you treat this with, say, something like sulfuric acid, H2SO4, you will begin to start protonating the alcohol. And once you protonate the alcohol, as we discussed yesterday when we were talking about Rennedy's chemistry a little bit, what then can happen? Lots of stuff, right? Yeah. You can start doing lots of stuff. You can start leaving, right? You can start transitioning that hydrogen somewhere else. It can maybe protonate something else intermolecularly. But yeah, so you can protonate, it becomes an electrophile or a leaving group, I guess more generally, so this way it becomes a leaving group. And so the overall system starts becoming more comparable to, say, for example, a halogen or something like that, except that it's a little bit more complicated because, again, the reverse would be pretty easy to do as well. So pKa in this degree, we're talking about around -2 or so. I got the exact value, but it's somewhere around there. Now, if you're going to start a deprotonated, that's oftentimes the one that you guys are always thinking about, right? Because we don't have solutions of, we do, HCl and HBr kind of solutions of H3O something minus, but we generally think of those as an HBr solution or HCl solution. I think one of the reasons why you guys often think about the higher pKa of water is because you're more comfortable thinking about things like sodium hydroxide, sodium methoxide, right? And so the pKa of those is much higher, right? It's about pKa of about 15 or so, right? And so, in that extent, we're going to deprotonate this, right? And let's just say M plus, right? And that's going to be our counter ion. Usually it'd be something like sodium or a lithium or a potassium or some other metal. And so, that's not that, when we think about in the grand scheme of things, the challenge with water is it doesn't take that strong of a base to deprotonate water. You guys think about sodium hydroxide as being a strong base. We're going to learn about a heck of a lot stronger bases than that. Our amides, our NH2 minuses, have pKa's of over 30, right? Our butyl lithiums, right? Our alkyl-based nucleophiles have pKa's approaching 50. So these are much, 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 much stronger. You treat one of those guys with an alcohol, and you might have an explosion in your lab because it's going to be so exothermic. So in general, the way in which we will generate alkoxides is there's a couple different ways that we can do it. But if you wanted to say, for example, generate an alkoxide, usually the one that you'll see in the book mostly is the sodium-based one. And that's probably one that you guys are comfortable with thinking about, because sodium methoxide or sodium hydroxide is something that you see. But how would you get to, say, sodium hydroxide? Now, maybe you read ahead in the book and you saw that the standard way to do it is with sodium metal, right? That's usually the cheapest way. It's a single electron process. That represents a mechanism that is not necessarily related to substitution, elimination, acid-base chemistry. But if you had to guess what kind of a base might do this, and you didn't read in the book, and you didn't see sodium metal, how might you propose to make an alkoxide, a sodium alkoxide? I just gave you one, right? Go to the higher pKa, right? Sodium amide, NaNH2, where the NH2 has a minus charge on it. Is that going to generate the alkoxide? Absolutely. One that might be that you should be able to figure out, but you might not be as familiar with, but the moment that I say it would make a lot of sense, is sodium hydride, right? NaH minus. And so if you haven't heard of sodium hydride, right, we can think about it as sodium plus H minus. Sodium hydride is one of these weird bases. I have to, for the life of me, and it's possible that I just haven't looked hard enough, and maybe I just asked people, nobody knows. But if you can find a pKa of sodium hydride, I'd be interested in hearing, because I've never heard of pKa of sodium hydride. And one of the reasons for that is, I think, to be able to measure something like that, you would need a reversible process. And what's going to happen the moment that sodium hydride reacts with, say, water, or, say, reacts with sodium hydroxide, the ethanol or something like that, what's going to happen? Yeah. It's going to be hydrogen gas, right? If the hydride is going to attack this, you're going to get hydrogen gas. And so I'm sure somebody out there somewhere has measured the pKa of sodium hydride, but you're not going to find it in your standard pKa tables that we go to on a consistent basis. It's probably out there somewhere. But there's a reason that we use it. Regardless of what the pKa of it is, it generates a gas. And what's the value, and how would that be beneficial, right? It makes it irreversible, right? So we were talking earlier about every single reaction being reversible. Well, in principle, every single reaction is reversible, but there are things that will just physically and technically render reactions irreversible. Generation of a gas that escapes the solution is certainly one way in which that happens, and that's something that's fairly common. So again, as you start reading through the chapter, you'll start noticing things like this. You'll start noticing we talked about TBS groups, so you'll start seeing the protection of alcohols with TBS groups to prevent things like that to happen. TBS, again, there's one last thing, and then I'll let you guys go, because we did talk about this yesterday. Here's a TBS group. TBS can come off under strongly acidic conditions, but it is fairly stable. What is nice about the TBS group, it comes off with fluorides as well. That's usually what you take it off with, is fluorides. But what's nice about that? First of all, it protects the deprotonation, right? Because now you don't have that there, it's just a big bulky silyl group. It might also prevent protonation, right? Because now you've got a big bulky group next to it that might prevent it from getting protonated. It turns out that you can actually deprotonate these under more harshly acidic conditions, but it will survive some fairly mildly acidic conditions. So anyway, so again, start figuring out these mechanisms of the different alcohol reactions. We're not going to go over them in class, but you're expecting them. Oh, one more point, because you guys do have the weekend. Organic chemistry is a cumulative course. It is not only cumulative of the material we learned this semester. As I've just illustrated, everything is based upon what we learned last semester. You are expected to know, it's not going to be emphasized specifically, but say, for example, synthesis problems. You're going to need to know every single reaction that you learned last semester. So if it's been a while that you took the course, try to catch up. Okay,